Okay, ladies and gentlemen, today we are going to be talking about conjugates. Conjugates are simply put, they're basically the same thing where we take a sign and change it around a little bit. If you notice here, we're going to take a complex number, and what we're going to be working with are called complex conjugates. So I take the real part and it stays the same, and I take whatever the imaginary part is, and what happens is whatever we start with, we change the magnitude or we change the sign of that imaginary part, and that's how we create something known as a conjugate. And since we're technically working with complex numbers, that's why we're going to refer to them as a complex conjugate. So a complex conjugate, it's really easy to do. For example, if I say 5 plus 3i, its complex conjugate would be 5 minus 3i. All we do is change the sign of the imaginary part, and that's it. If I started with negative 6 minus 2i, its complex conjugate would be negative 6 plus 2i. The real part stays the same, but the sign of the complex part of the imaginary part changes from whatever it was to its opposite. Now, one of the things that we're going to be using complex numbers or complex conjugates for is so that way we can try and create a real value from two complex numbers. And that's going to be demonstrated here very quickly. But what we're going to look at first here is we want to kind of see how are these terms going to get multiplied together. Here we have a pair of complex conjugates. I know that they're conjugates because the real parts and the imaginary parts are the same, but the sign of the imaginary part is opposite. So if we took two complex conjugates and we multiply them together, what we should be left with is nothing but a real value, a single real number. So here, we're going to treat this very similarly to any other binomial term that we would be multiplying together. Binomial obviously just meaning that we have two parts. So I'm going to take the a's and multiply those together just like a normal FOIL process, and that will give me a squared. I'm going to take this a, multiply it to the imaginary part here, and that would give me a negative a, b, I. Then I'm going to take the real part here, I'm sorry, the complex part here, multiply it to the a, and that would give me a plus a, b, I. And then here, the last terms together, positive times a negative will give me a negative, and b times a b will give me a b squared, and I times an I will give me an I squared. So in the middle, you can see the like terms. I have an A, a B, and an I. One's positive, one's negative. Those two are going to wind up canceling each other out, and I'll have an A squared minus B squared. And keep in mind from previous lessons, I squared is really just negative 1. So I'm going to replace I squared with negative 1 here, and I'm going to be left with A squared. So negative b squared times a negative 1 becomes a positive b squared, which the a and the b are both real numbers. So when I square them and I add them together, I'm going to be left with one individual number. So from taking complex conjugates and multiplying them together, we're going to wind up with a single number as a simplified number, as a simplified form. We'll be using stuff like this when it comes to polynomials, when we're trying to evaluate what are the solutions of a polynomial, because sometimes they have real solutions, sometimes they have imaginary solutions, and but we'll talk about more about that when we get there. So here we have a complex number, and we're squaring the complex number. Now this one is going to have a slightly different effect than multiplying complex conjugates. This example here is not one where I'm multiplying conjugates together. I'm taking a complex number and I'm squaring it. Now we're going to FOIL it just like what we did in the other example, but we're going to wind up with a slightly different expression at the end. So the a times the a gives me a squared. The a times the last bi gives me plus a bi. The bi in the first term multiplied to the a in the second term will give me another positive abi, and then b times b will give me plus b squared, and I times I will give me I squared. So let's simplify it as much as we can. A squared is just a squared. In the middle, anytime we FOIL, the two terms in the middle should always be like terms. So I have an ABI plus ABI, so it's going to give me two ABI terms. And we have B squared, but remember this I squared is just negative 1. So I'm going to substitute negative 1 for I squared. And that's going to give me a squared plus 2abi minus b squared. And this is the simplified form of when I square uh, a complex number where I'm adding the complex part to the real part. So if I had an example where I'm squaring one where I'm adding the complex part to the real part, what happens if I'm subtracting the complex part? So let's try working through that one here real quick. A minus bi again, because we're squaring the complex number. So a times a will give me a squared. The first a times the second negative bi will give me minus a bi, and then the bi from the first term times the a of the second term will give me another minus a bi, and then negative b times negative b will give me a positive b squared, and the I times I will give me an I squared. And so again, let's just continue simplifying. Our like terms in the middle, negative ABI and negative ABI will give me negative 2 ABI when we combine them. And so plus b squared, but again, replace the I squared with negative 1. And finally, a squared minus 2abi minus b squared. And so this would be the final expression when I square a complex number where the complex part is being subtracted from the real part. The whole point of showing you those three examples is because they follow the same pattern no matter what complex numbers that we have. So it may be possible, it may be more convenient for us at times to simply look at the rules that are generated for those particular combinations rather than having to FOIL them each time. If we know the value of the A term and the value of the B term, we can simply go to each of these three individual rules and simplify it without necessarily having to go through the FOIL process. Now, I will go ahead and FOIL some of these because I understand some of us are going to have a difficult time seeing it, and you're going to need to see the FOIL process. Some of us are going to be able to use the rules no problem, so I'm going to start using both examples here. Now, let's take a look at this next example. What it's asking us to do is says name the complex conjugate and then find the product of both of the complex numbers, the one that was given to us and the conjugate that we come up with. Well, the conjugate of this, all we have to do is just change the sign here. So that's going to give me a negative 1 minus I times radical 5. Okay, so let's look at it through the FOIL process because this is the tried and true method. We don't have to remember any shortcuts or anything like that. We can always FOIL numbers together. We've been doing it for a long time. So write down the original one that they gave us, negative 1 plus I radical 5, and we're going to multiply its conjugate, negative 1 minus I radical 5. So if we multiply these together, negative 1 times negative 1, that's just 1. Negative 1 times negative I radical 5 will give me a positive 1I radical 5. And now positive I radical 5 times negative 1 will give me negative I radical 5. And the last terms together, positive I radical 5 times negative I radical 5 will give me positive I times negative I will give me negative I squared. Radical 5 times radical 5 will give me radical 5 squared. So in the middle, the two like terms, the positive and the negative I radical 5, those are going to cancel each other out, and I'm going to be left with 1 minus, so the square, or I squared, that's just negative 1, and the square root of 5 squared is just 5. So in the middle here, we have 1, negative times negative will give me a positive 1, and positive 1 times 5 just gives me 5. So the whole thing simplifies to be one whole number, which is what we said should always happen when we multiply conjugate pairs together. So let's try it the other way, looking at just the rule. So the rule says if I multiply complex conjugates together, I'm going to just say a squared plus b squared. Well, the a term is 1 or negative 1, however you want to think of it. So if I say negative 1 and I square it, okay, and then look at the b term, the b is not the I, it's the actual real number, the square root of 5. So I'm going to say the square root of 5 squared. Well, negative 1 squared is 1. Square root of 5 squared is just 5. And that gets us to 6 with a little bit less work and possibly less issues with confusing signs at some point. So I just want to demonstrate how the FOIL method is being used. We know how to use it. We've used it quite a lot in previous math classes, but that rule, it could be a little bit of a time saver as long as you remember what it is. So now let's take a look at this one. So here we have fractions, which again, some of us might be having mild panic attacks here. Now, this one I actually might work out 3 different ways for you, because some of us are going to be tempted at this point to try to get rid of the denominator with, or try to get rid of the fractions completely with the lowest common denominator, which would be great if we were working with an equation. This is not an equation. There's nothing saying this is equal to something else, and we're trying to solve for a variable. Now, that isn't going to be completely wrong. However, it will be easier to see what happens when I multiply with the lowest common denominator, in this case, if I don't do it first. So just trust me as the professional here that let's just look at it the way it is first. Now, here, let's come to one side of the screen, and we got 3 over 4 plus 1/5 I. Well, its conjugate pair, its partner, is going to be 3 over 4 minus 1/5 I. Now we can do this again both ways. We can FOIL it because we're used to FOILing, or we could use the rule. So I'm going to just FOIL first and see what we get. 3/4 times 3/4 gives me 9 over 16. 3/4 times negative 1/5 I will give me negative 3 over 20 I. And then next we're going to get 1/5 I times positive 3/4, so that'll give me positive 3 over 20 I. And then the 1/5 together will give me a negative 1 over 25 I squared. Okay, now again, the two terms in the middle, those cancel out, so I'm left with 9 over 16 minus 1 over 25, and we're going to replace the I squared with negative 1, and that'll give me 9 over 16 plus 1 over 25. And at this point, really, we just want to type that into our calculator. We're not going to worry about actually figuring out what the common denominator is. And if we type that into our calculator, we're going to get 241 over 400. or as a decimal, this one is not a bad decimal, 0.6025. Okay, so let's take a look with it using the particular rule where we just said a squared plus b squared. Well, a is 3/4, so I'm going to say 3/4 squared. B, the b term is the 1/5, so 1/5 squared. So again, this is just going to be 9/16 plus 1/25, which again, when you type it into the calculator, is 241/400. And let me clean that up just a bit because I touched the board and it almost looks like that's a negative. So last thing, let's try one more here. Let me pick a different color so that way it'll try and differentiate it just a little bit. Oop, come on, work with me here. Let's go with purple. So here, now I want to say, okay, if we started this problem out, particularly because we've done it recently, by saying, well, I don't like fractions, I hate fractions, let's get rid of them. Okay, you can work this out with a common denominator, but there's a little catch to it. And the reason why I wanted to do it the way I did it first is to explain what the catch is here at the end. So the the smallest common denominator between the 4 and the 5 is going to be 20. So if we want to, we can multiply through with that with 20, and this is going to give me 15 plus 4i. Now here, again, if we use our little rule that says a squared plus b squared, I'm going to just say 15 squared plus 4 squared. 15 squared gives you 225 plus 16, which happens to work out to be 241, which, if you notice, is the same as the numerator that we got in either of the two ways that we did it before. So we can start off by getting rid of the common denominators, but if we don't have an equal sign, if we're not actually saying something is equal to something else, by getting rid of the common denominator, by getting rid of the denominators completely, we're not keeping it proportional. So we have to keep that over whatever this was, squared, which happens to be the 400 that we had in the denominators originally. So you can still do the get rid of the fractions with the common denominator trick that we worked on with our equations, but it might not work out for you if you don't remember that they're not proportional, so we have to work the denominator back in at some point. So next example here is just says, well, find the complex number again, or find the complex conjugate again, and then multiply it. Well, here, this is just 5i. That's the complex conjugate. So if I multiply those together, I'm going to get negative 5i times positive 5i. So the negative 5 and the positive 5 give me negative 25. I times I gives me I squared again. And I squared is just negative 1, so ultimately we're left with just 25 for that particular example. Nice easy one because it's just the complex part. There's no real part that we have to worry about. So here we have an example that's written strictly in its complex conjugate form already, where we have, we're given negative 7i, so its conjugate would be the positive 7i. In this case, I'm going to go ahead and, again, FOIL it out one way and then use the rule the other way, just for anybody that needs to see it. Either way, I want to make sure I'm not leaving anybody out. So the negative 2 times negative 2, that's going to be 4. Negative 2 times positive 7i will be negative 14i. And then we'll get a positive 14i I when we multiply the negative 7 and the negative 2. And negative 7 times positive 7 will give me negative 49I squared. So negative 14 and positive 14 cancel each other out, and I'll be left with 4 minus 49, and I squared changes to be negative 1. So we have 4 minus 40 plus 49, which is going to be 53. I don't know why I can't write right now, but 53. And if we do the a squared plus b squared thing, if you notice, a in both of the expressions is a negative 2, but the b in one I have a negative 7 and the other one I have a positive 7. But it doesn't really matter what the sign is because when we square it, it still winds up to be a positive number. So here I'm going to put the negative 2 and I'm going to square it. Here, let's just say negative 7, just why not? It doesn't matter because whenever I square a negative number, I wind up with a positive number anyway. So I get 4 plus 49, which still gives me my 53 for my single real answer, or my simplified answer, I should say. Here, again, square it. So we have negative 3 plus I times negative 3 plus I. And the negative 3's multiplied together give me a positive 9. Then I'm going to get minus 3I, and then another minus 3I, and then positive I squared. So the like terms, again, come from the middle two. So I'm going to get 9 minus 6I, and then the I squared becomes a negative 1. So that's going to give me 8 minus 6I as the final simplified answer. Now let's take a look at our rule here. When I'm squaring something, when I'm squaring a complex number where I'm adding the complex part to the real part, remember that gives us a rule of a squared plus 2a bi minus b squared. So here, a, well, that's just the 3. So I say negative 3 squared plus 2 times negative 3. The real part of the complex I term is just a 1, and minus 1 squared. So that gives me 9. Oh, and I forgot my I right there. So 2 times negative 3, that's negative 6I. And of course, the minus 1 still gives me 8 minus 6I when I combine my like terms. So whichever way you feel that you prefer, using the FOIL method or using the rule that we established for that one. So let's take a look at this last example where we're taking the difference of the real part and the complex part. So, or the imaginary part. Let's go ahead and FOIL it for the first time. And 5 minus I square root 3 times 5 minus I square root 3. 5 times 5 is 25. 5 times negative I radical 3 will give me minus 5I radical 3. And then negative I radical 3 times the 5 will give me another negative 5I radical 3. And then negative I times negative I will give me positive I squared. And the radical 3 times the radical 3, that's going to be really just a 3. So again, the like terms come from the two middle when we FOIL things. So 25 minus 10I radical 3 plus I squared is negative 1. Negative 1 times 3 will give me a minus 3. So let me change that sign here. So that's going to give me a minus 3 here, which will ultimately just give me 22 minus 10I radical 3 when we combine the like terms of the 25 and the 3. Now the last little rule that we got from the first examples that we did, when I multiply or when I square a complex number where I'm taking the difference of the real part and the imaginary part, that gave us a rule that said a squared minus 2abi minus b squared. And so let's just substitute the values to see, maybe you prefer one versus the other. I always tend to do foiling simply because I do it all the time. We foil so much, and the rules are a little particular, but if you remember them and you want to use them, please, by all means, go ahead. So we're going to take the a term, which is the 5, and square it, minus 2 times the 5. Now the b term, the real part of the imaginary number that we have there, is the square root of 3. So I'm going to put the square root of 3 in there for the b, and then I'm going to say minus the square root of 3 squared again for b. So 5 squared gives me 25. Negative 2 times 5 will give me negative 10. And I'm going to put the I, radical 3, because if I put the I at the end where the radical 3 is, sometimes people think that the I is underneath the square root symbol. So I like to keep the I in front of the square root symbol. And then minus square root of 3 squared is just 3. 25 minus 3 gives me another 22 minus 10i radical 3. So make sure that you've been taking good notes on these. We are going to be working on this lesson during your one of your next upcoming classes. If you have any questions, please make sure you come see me. I will be more than happy to help you with any questions that you may have. But in the meantime, take care. See you soon.